Paper chromatography is a partition process, in which paper acts as a solid support and the stationary phase. It can be run as either a descending or ascending chromatograph, depending on which edge is emerged in the solvent/mobile phase. Paper chromatography is the simplest form of chromatography and separates components based on their interactions with the solvent and the paper. Say you find a note at a crime scene written in black ink and take the pens from the 8 suspected authors of the note. To identify which of the pens wrote the note, we can use paper chromatography. Firstly, we draw a pencil line at the bottom of the paper and dissolve the ink from the note in the minimum amount of solvent and place a small spot of it on the pencil line, marking this as a reference. Then, draw a small spot from each pen on the pencil line, being careful to label each in pencil so you can ID the pen correctly at the end. You would then put the paper into a beaker containing solvent, and covered, the paper is left in the beaker until the solvent is almost at the top of the paper, at which time it is removed, and the solvent front is marked in pencil. As this example uses coloured components, it should be clear which pen/person is the culprit. An RF value is measured by measuring the distance that the spot has travelled from start line to middle of the spot, and dividing it by the distance from start to the solvent front. RF values are not always the best way to work out what the sample is made up of, as it relies on the quality of the paper, the humidity of that day, and the temperature, and various other things that are hard to control. Generally, repeating the chromatograph with different solvent and measuring the RF values can be quite accurate, as you can compile and get a more accurate result if 2 or more agree with the reference values for the RF of that solvent. For colourless components, you can use a UV light to see the spots or introduce a chemical that produces colour. For example, take amino acids. They all produce colourless spots, but when the paper is allowed to dry and then sprayed with ninhydrin, it changes the colours of the amino acids to brown and purples, which can be compared to known colours and patterns for the amino acids already recorded. Another way to get a more accurate result is two-way chromatography, in which you can separate the compounds of similar RF. You run a normal paper chromatograph, but this time you mark the solvent front as SF1, and then let it completely dry before rotating the paper 90 degrees and running it again in a different solvent. As it's highly unlikely that two components will have the same RF values in two different solvents, so you get two spots, as well as you can measure two sets of RFs and look them up compared to the known values in the database. When choosing a solvent for the separation, you need to consider what will be in your samples and choose a solvent that's appropriate. A typical procedure for unknown samples is to try a few solvents over the range of polar to non-polar. The main thing that is important is that the system is under saturation. This is something that is usually achieved by carrying out the separation in a jar or covering the beaker with a watch glass. Cellulose paper is the most used type of paper in this method, although others are available and used, i.e. glass fibre paper. It is popular because it works well and can be modified to improve resolution or make spots more clear. As you could probably guess, cellulose paper is made up of cellulose fibres. The polymer chains of cellulose have OH groups pointing out that can attract the water vapour from the atmosphere and bind to any vapour around when making the paper. In actuality, cellulose paper works as a chromatographic paper because it is a paper with a thin layer of water on the surface, and the interactions during the separation are as a result of the water and not the cellulose itself. If a non-polar solvent is used with cellulose paper, the non-polar solvent won't be attracted to the water on the cellulose and will spend most of its moving time dissolved in the solvent, and so will move quite high up the plate, whilst polar molecules will be more attracted to the water than the solvent and dissolve into the paper instead, not moving very far. Because the components divide their time between two non-mixing solvents, a partition is formed, hence why this combination of cellulose paper and non-polar solvents is called partition chromatography. If water is used as a solvent, then it becomes both the stationary and mobile phase. This method produced components with different RF values to each other, so the two types of water must interact in different ways. But there has not been an absolute explanation as to what these ways are. Some rather complex mechanisms have been proposed, but it's probably advisable just to accept that it works and it's beyond the scope of this course.